Our next speaker is Benjamin Farr. Benjamin is giving a talk on electron beam dust mitigation method for lunar surface exploration.
All right, does everybody hear me? Okay.
Yes.
All right, thank you everybody for coming to listen to my experiments of dust mitigation for lunar surface exploration. I'll be talking about several experiments that we've done, actually. So, hang on, let me make sure. Okay, cool. So the motivation for the experiments is, of course, lunar dust regolith has been shown to be an issue for lunar exploration. It causes damages to spacesuits. It causes issues for solar panels and thermal radiation. It causes issues with mechanical equipment, and it can also cause issues for just astronaut health. So we'd like to get rid of that dust, and that is what me and my team have been working on for the last couple of years. So our theory is our experiment is based on a theory called the patch charge model. And the patch charge model was developed to explain electrostatic dust lofting due to solar wind exposure and UV radiation. So the theory postulates that if you have a dust layer, there are microcavities between all the dust particles. And when the dust is bombarded with UV radiation or solar wind, that generates secondary electrons or photoelectrons that are emitted from neighboring particles, and those build up inside those microcavities and eventually gives you a really large negative force, which then forces the particles to jump away from each other. So that's what we're basing this dust mitigation method on. So our experiment, we are using a hot tungsten filament to create an electron beam, and we are just shooting that beam at a dust covered substrate. And we've tested everything inside of a vacuum chamber where we feed in about 10 to the minus 4 torr of gas just to create a plasma background for the electrons to actually travel through. In the first experiment, we were trying to figure out a whole bunch of things. We're trying to figure out the optimum beam parameters. We were trying to figure out how different materials react to this cleaning method. We were trying to figure out how the initial thickness of the dust layer impacts everything. So we just wanted to understand if this is actually something worth pursuing. So the setup we have inside the chamber, we have our dust covered sample tilted 45 degrees to the filament. And then to record the data, we just record a video of it and we analyze that video data. And here's a quick video just to show how much the dust actually reacts to an electron beam. So that is the dust hopping around. And then these images here show a before and after shot of a glass slide that was covered in dust. We expose it to the beam and now it is no longer covered in dust. So that's pretty cool and good results for us. So the first test, we wanted to see the current density and how that affected the cleanliness. And we found that for anything above about 0.3 microamps per centimeter squared, we get the same final cleanliness. The only difference is the cleaning time. So for all the tests after that, we ran about 1.5 micrograms per centimeter squared. We also tested the beam energy. We tested 8 electron volts, 150 electron volts, and 230 electron volts. And we found that it actually does get a little bit cleaner every time we increase the voltage. We tested glass and spacesuit materials and found the glass was a little bit easier to clean than the spacesuit. And we believe that's because the spacesuit has a whole bunch of little pockets for the dust to get inside of, so it's just a little bit harder to clean. And then we also tested the initial dust layer thickness. So we tried a thin layer, a medium layer, and a thick layer. So 0%, which is completely covered, 40% clean, which is about 60% covered, and then 60% clean. And we found that the thicker the dust layer is, the harder it is to clean up, which kind of made sense to us. So this is just a quick slide going over the results. I'm going to skip over that pretty quick. Our current experiment that we're working on is trying to optimize the results even further. So everything we found in that last experiment showed that we could get about 80% cleanliness. So we wanted to try and get rid of that last 20%. And we were hoping that to get rid of that last 20%, we can rotate the sample relative to the beam source, which would change the angle between the beam and the dust. And the idea is that allows different microcavities to be exposed to the electron beam, allowing us to just clean off more dust. And we did do some preliminary experiments, just rotating the sample without a beam to show that no dust falls off just based on the rotation, the vibrations, the gravity, and nothing fell off, so that's good. So we're confident that any increase in cleanliness is just because of the changing angle. The only thing that we changed for this experiment was that we attached the sample to a DC motor that rotated it at 6 RPM. We would rotate for 2.5 minutes exposed to the beam and then stop for 2.5 minutes. And in that 2.5 minutes pause, we would take our data. And we tested glass first. And for every test, we would let the process go without rotating. Then once it stopped, then we would start rotating so that we could see exactly how much the rotation helped. So for glass with a thick layer, we found that we got an increase of about 20% with the rotation. So we jumped from 60 to about 80. And then for a thin layer, there wasn't really too much increase with the rotation. And we think that's just because it was already so clean in the first place. Pat ourselves on the back. So for the spacesuit, we found that for a thick layer, we also get about a 25% jump in the cleanliness. So it jumps from about 55 to 80. And then for a thin layer, we go from about 65 to 85. So both cases, that's good. We see some sort of increase in the cleanliness when we start the rotation. And then we also tested a photovoltaic solar panel with this rotation method, and that wasn't quite as good. So we found that for a thick layer, we get about a 10% increase from maybe 45 to 55%. But then for a thin layer, we don't really see too much change at all. And that's just because the actual solar panel is very, very adhesive to the dust. And we have yet to discover why. That's something in the future. So to summarize real quick, we're very happy with our results. With the rotation method for glass and spacesuit, we're able to get about 85 to 90% cleanliness, which we're very happy with. The solar panel was not as good. We got about 63% max. So we still want to work on that a little bit. Yeah, and then for our future experiments, we're going to continue testing other materials. We're going to test ITO, we're going to test a thermal blanket, Kapton tape, aluminum, stainless steel, and really anything else that we can think of that might be worth testing. We are also going to look into testing, instead of rotating the sample, we're just going to set up multiple beam sources. That way we can simplify the experiment a little bit and just have different beam sources oriented differently to the sample. And then way in the future, we're also going to test if this method works for mitigating Martian dust. So that is going to come in a couple of years. That is all I've got. Thank you very much. I can answer any questions if you've got any. If not, thank you.
Very interesting. Thank you, Benjamin. Nice talk. I don't see anything in the chat right now, and encourage people to pop questions in there. I do have a question for you.
Yeah.
I may have missed this, but can you tell us a little bit more about how you prepared or distributed the dust on the surface, and did you do anything in terms of sifting or grinding or anything like that to prepare your specimen in advance of the study?
Yes, sorry, I was trying to rush through all these slides and I forgot that part. But yes, so all of our tests, we did them with a JSC1 lunar simulant that was sifted down so it was all less than 25 microns. And then to deposit the dust onto the sample, we just sift it straight onto the sample to try and get it as evenly distributed as possible. And then as far as determining like the initial thickness of the layer, we wrote a program so that we can just take a picture of the background, then take a picture of the dust layer, and then that'll tell us how thick we're starting out. Yes.
Great,
sorry.
thank you for that. No, that's very good. And if you mentioned it, I missed it because I'm juggling a bunch of things here. We do have one more quick question. One of them is how are your cleanliness percentages calculated and how much power is required? Do you want to take a stab at that?
Yeah, so the cleanliness percentage, we calculate that just by an image subtraction, basically. So we take first a picture of the completely clean sample, and then we take a picture of the sample completely covered in dust. And then we use those to basically subtract the images of the sample throughout the test. So we take a picture every 1 second, and that's how we got those plots. So every frame we have the test data, and then we compare that to the clean and the completely covered data, and then that gives us our total number. And it works well for glass and spacesuit because the glass we just put on a white background and the dust is gray, so that's a pretty good contrast. Same thing for the spacesuit. Some other materials we're testing, we might need to come up with something different because like thermal blanket is basically just orange foil. So that doesn't have a very good contrast. So we're struggling with that right now. So, but yeah, it's just an image comparison.
Great, thank you.